All right, ladies and gentlemen, class recording for today has started. So, yesterday we introduced a concept important to the idea of calorimetry, where we are going ultimately to measure how much heat energy is exchanged between different objects. And we talked about in the first outline that concept of heat energy being transferred because of a temperature difference, hot to cold, they end up the same temperature, blah, blah, blah. Now we want to take it from qualitatively describing what would happen to quantitatively measuring what's happening. How much energy are we actually moving around? And before we can actually make that calculation, we have to talk about the materials. And the materials that are involved gets us into the specific heat. So we define specific heat as the amount of energy needed to raise the temperature 1 gram of material by 1 degree Celsius. So it's how easily does something heat up or cool down. Yesterday we talked about a couple of examples. Tell me about how the specific heat relates to the temperature change of that object. Describe that for me. Say it again. Good. If something has a higher specific heat, it takes longer to heat up, but that also works the other way around too, right? It also takes longer to do what? To cool down if it already is hot, right? Things that have lower specific heats are relatively easy to heat up and cool down, right? And so yesterday we talked about these examples, right? We talked about this with pizza rolls, or somebody else in the other class brought up hot pockets. This happens with all the time, right? Okay. You put that hot pocket in the microwave and you cook it, and it feels fine. You pick it up, you bite it, and then what? Yeah, you have to, because that middle stays hot for a long time, right? And so, yeah, if you cut it open, obviously that will work. Yeah.
What's that hot pocket?
I don't remember. So,
John.
So, actually, I think it was John. Actually, so, is he famous for hot pocket eating, or you know? So,
I just like saying John.
So, all right. So anyway, with this, right, because the filling of the crust stays hotter. The filling stays hotter than the crust because it has a larger specific heat, okay? Or the filling of the hot pocket, the other thing, did we talk about toaster strudel in here? Oh, we did talk about toaster strudel, right? Yeah, sorry, I didn't mean to bring up bad memories. I couldn't remember which class we talked about toaster strudel in, and I don't want you to go off again, you know. So, but anyway, but then on the other hand, did we talk about the beach? We talked about the beach, right? Did we talk about the desert?
Oh, yeah.
Okay. That the desert, we think of it as being really hot, but it actually has large fluctuations in temperature because sand, generally speaking, has a low specific heat, right? So, finally, before we move on to actually calculating, there's one thing that when we look at the different materials, this quote sums up a lot of what we do here. It says water is king when it comes to specific heat capacity. So, implying what about the specific heat capacity of water? It's really high. It might not be, it's not the highest thing out there, but it is on average really high, a lot higher than other things, right? Let's take pizza rolls as an example of this, right? The dough of a pizza roll is made up of flour and, you know, those kind of things. But the sauce inside of a pizza roll, right? Sauce is basically what? Water, right? Flavored water, right? What? Well, tomatoes are basically what? Water, right? Okay. So it's, it's tomato sauce, yes, but that's basically water. So that inside stays stays hot for a long time because it is water, right? So tomorrow, if you've looked at the weather forecast, tomorrow the high temperature is only supposed to be about 30 degrees, okay? Which I think most of us know is below the freezing point of water, yes?
Yeah.
Is the lake going to freeze tomorrow because the temperature is going to be low? No, it doesn't, right? Because, well, what's the lake made out of?
Water.
Water, right? Water has a really high specific heat, meaning, right, it takes a long time to heat up, but it also takes a long time to cool down. All summer long, the lake has been absorbing energy from the sun, and that causes it to heat up. Now, even though the air surrounding it is very cold, water will hold on to that heat and will gradually get cooler, right? Does the lake eventually freeze over? Yeah, eventually it does, but it usually doesn't happen until like January or February because it takes a long time for it to get down to the freezing point of water, right? Now, it also works the other way, right? Let's say it's May 1st. We might have a really nice day, like it might be 70 degrees on May 1st. But if you go to the lake, right, what's the temperature of the lake going to be? Like 40, you know? Yeah, it's going to be freezing, right? Which then leads us to certain weather patterns, right? So, you guys may not have experienced this yet, but if you go, does everybody know where Bay High School is? Right? Or Avon Lake High School. You know where Avon Lake High School is too? If you go there in the spring for a baseball or softball game or a track meet or something like that, it is freezing. Because it's right next to the lake. But in the spring, even though it might be a really nice day, right? What's the temperature of the lake? It's still really cold, right? So that cold air coming off of the lake makes it seem really cold. Even here, just going north, whatever it is to get to Bay High School, right? Bay High School, if you look at the map, is almost directly north from us. It's actually pretty close to being directly north from us. But it's like 3 miles north. That makes a big difference, right? I used to teach at Avon Lake High School before I came here for a couple years. And in the springtime, you'd see kids like that would come from North Olmsted or Olmsted Falls, where it might be like 65 degrees to like play softball or something like that, and they'd get to Avon Lake and it's like 45 degrees, and none of them had sweatshirts or anything because it was really, really warm when they left, right? But another thing that this contributes to is lake effect snow, right? Which we're supposed to get some tomorrow, but we're probably not going to get any here because we just don't. Right? So anyway, see, it's like a trade-off. If you're in a place that gets a lot of lake effect snow, for like if you go to Chardon or something like that on the east side where they get a lot of lake effect snow, if we get 6 inches of snow overnight, we might have school canceled. But if they get 6 inches of snow overnight, they're used to it. So it's like, oh, the guys just go out and plow the road and everything's cool, and you know. Right? Now, like if you go, anybody ever lived down like south, like Tennessee, Atlanta, or anything like that? Like literally, it's actually even in Cincinnati, like even the southern part of Ohio. If they get like an inch of snow, it's like, oh my god, apocalypse. So. Yeah. Not exactly. One of my friends from college lives in Atlanta, and I think it was 2 winters ago, because last winter nobody got any snow anywhere, right? But like
one snow.
Yeah.
It shouldn't be.
So, I mean, it literally only snowed like 3 times last winter.
Didn't the high school not even have one?
Yeah.
They had that day off anyway.
Yeah, we had like snow. Yeah, we had like conferences that day. I think. I did not use my snowblower at all last year. Like anytime it snowed, I just like it's going to be more trouble getting my snowblower out than just using the shovel to push it off the driveway. But a couple of winters ago, it was pretty bad. We had like a couple snow days that were really cold, and my friend from Atlanta, like I don't know if you guys remember or not, but Atlanta got like 2 inches of snow, and literally like the city shut down. Like not joking, like the city shut down. People were like, they were reporting, if you looked at the highway, people were just like abandoning their cars on the highway because they had been sitting there, or there were these stories of people who had been in their cars for like 24 hours on the highway. And I'm thinking to myself, okay, it's 2 inches of snow, just walk. Like, I mean, if you've ever been to Atlanta before, like the highway that runs through Atlanta is huge. It's like a 5-lane highway in both directions. but there's got to be like something on the side of the road, like people or a gas station or something. It's 2 inches of snow. Just walk. Why would you sit in your car for 24 hours? Like I don't. So I wrote to him and I'm like, hey, is this like legit? Is this like a real legit winter thing, or are people just don't know what to do because it snows? And he's like, kind of both. Like it's kind of snowy, but he's from Pittsburgh and he's like, yeah, it's not like real winter. It's just Atlanta people. So but whatever. So lake effect snow, right? Lake effect snow happens when 2 things are true. 1, the lake is not frozen, and 2, it's windy. Those are the 2 requirements that we need for lake effect snow. Okay? So the lake is not frozen. If the lake is not frozen, that means it's still, relatively speaking, what? Warm, relatively speaking. Okay? If you go up to the lake now and jump in, it's not like it's bad, right? It's pretty cold, but it's still warm, right? Then the wind comes along and blows across the lake. Because the lake is not frozen, it's still evaporating, right? So that wind comes across the lake and the evaporated water gets picked up by the wind. And then the wind continues to blow across the lake and it gets off of the lake and it hits the land. But as we discussed, what's the temperature on land going to be tomorrow? 30, right? Below freezing. So all of that moisture that the wind picked up as it was going across the lake turns into what when it gets to the cold air? Turns into snow, right? When the lake freezes over, do we have lake effect snow? No. We don't have lake effect snow anymore when the lake freezes over, right? But as long as the lake is still liquid and still evaporating, that air that passes over the lake picks up that moisture, and once it ends up on the cold land, it dumps it out as snow. 2 reasons why we don't get a lot of lake effect snow here, right? 1, the way the wind blows in the wintertime, it usually blows from west to east, so the wind kind of passes over us, right? Or where the wind blows from, it doesn't really hit us all that much. But 2, Bay Village or Avon Lake, they don't get lake effect snow because they're too close to the lake. It takes a while for that moisture to fall out in snow. It doesn't happen right at the edge of the land. It has to get cold and then snow. So, places that are a little bit off the lake, if the wind blows right, Strongsville gets like tons and tons and tons of lake effect snow if the wind blows the right way. If you look at the places that get lake effect snow, they're not right along the coast. It's things that are a little bit inland, so the moisture that the wind picks up has a chance to turn into snow. Right? But to answer the last question, right? Explain what the girl means in her statement by using some practical examples. Water is king when it comes to specific heat, meaning water has a very high specific heat value, right? And that basically can mean 2 things for us, right? What does it mean about water having a high specific heat? That means it does what? Takes longer to warm up, but it also takes longer to cool down, right? So we talked a little bit about, right? The fact that the lake stays liquid longer in the wintertime, but it's still cold in the spring, right? Anybody ever been to San Francisco before? San Francisco's cool. It's cool. It's like one of my favorite places to go visit. But it never gets what Alcatraz is kind of cool. Although if you've been to Alcatraz like once or twice, you're kind of like, okay, I'm kind of good. It stunk. It stinks to be a prison, but yeah, it's a prison, so But San Francisco, right? If you've ever been to San Francisco before, it never really gets colder than 40, but it never really gets warmer than 70. Because the water that surrounds it, it's a peninsula, and the water that surrounds it keeps the temperature somewhat constant, so it doesn't have wild fluctuations. So, all right, good there? Okay. Specific heat relates to a substance. Each substance, each material has a different specific heat value, meaning that it heats up and cools down at different rates. And that can affect how much its temperature goes up and down. And we measure the energy changes that are involved with this equation. So Q is equal to M times C times delta T. You don't have to put all the multiplication signs in there if you don't want to. Like on your outline, it just says right there. Okay. So let's take some guesses. First, I hope we know what M is probably going to stand for. Mass. All right. So M is going to stand for mass. Okay. Delta T, change in temperature in this case, right? Because that's what we're worried about. And if we're calculating the change in anything, right, how do we do it? How do we
Final minus initial.
Final minus initial. So delta T is the same as T final minus T initial. Or what is the final temperature minus what is the initial temperature? All right? So let's talk about the other two things. C. C stands for the... Did you want to? No. It doesn't stand for Celsius in this case. C represents the specific heat. Okay? So C is what we use to represent the specific heat value. Alright? And then Q represents the actual amount of energy, or thermal energy, that an object either picks up or loses depending on whether it's heating up or cooling down. Okay? Okay? Good with all those things. Got that? All right. Let's transition to the sheet that I gave you today, the packet that has a couple of calculations, and let's see how this all fits together. Okay? All right. We are going to actually start on the back page. We're going to start with exercise number 5, because I think it's more conceptual than anything. So, exercise number 5 says, a silver coin and a gold coin. What? Well, it's page 3 of that packet, but there's nothing on the back, so it's actually the last page of the packet. All right, so it says, a silver coin and a gold coin each have a mass of exactly 6.6 grams. The specific heat of silver is 0.235. The specific heat of gold is 0.130. Which coin requires more heat to raise its temperature by 40 degrees Celsius? So let's even answer this question without doing any calculations. Jack? Silver. All right? Jack says silver. Okay? Jack is right. Let's talk about why Jack's right. Why is Jack right that silver is going to require more heat?
It has a higher specific
Higher specific heat. All right? Things that have higher specific heats are what?
more resistant
More resistant to
to temperature.
temperature changes. It's actually a really good way to word it, right? So, because silver has a higher specific heat, right? Okay? Because silver has a higher specific heat, increased specific heat leads us to harder temperature change. Right? It's going to require more energy for it to go up 40 degrees Celsius because it's harder to get it to change its temperature. Good with that? All right. Let's take a look now at question or exercise number 2. It says, Tori wants to increase the temperature of 500 grams of water from 20 degrees Celsius to 100 degrees Celsius. If the specific heat of water is, that's basically boiling water because water that comes out of the tap is about 20 degrees Celsius and 100 degrees Celsius is the boiling point. So she wants to boil some water. How much heat is needed? So, if it's asking us how much heat is needed, what letter are we trying to solve for in that equation that I just gave you?
C.
No. Q. Right? How much heat? Heat is a form of energy, right? So it's asking us to solve for Q. All right, What else did they give us in this problem? Whoa, whoa, whoa. They gave us, oh, go ahead.
Mass.
Yeah, they told us.
Specific heat and the change in temperature.
Well, so they gave us the mass, and they straight up gave us the specific heat, 4.81. Let's go, we're going to go with this crazy unit, and I'll tell you how this unit is, right? So that's just the unit, okay? Now, did they actually give us the change in temperature? But they gave us enough to figure it out, right? What is the change in temperature going to be in this case? 80 degrees Celsius. Now, one thing that's going to be important now when we talk about this, right? When you calculate it, right? This is final, this is initial, so when we plug it in there, we end up with a positive number, right? That's going to be important because sometimes we'll have things heating up, but if something is heating up, what has to be happening somewhere else? Something else has to be cooling down. So let's keep our positives and negatives here, even though these are scalar quantities, right? Then we still have to know whether they're getting bigger or smaller, okay? All right, so we just learned that to figure out the amount of energy, we multiply the mass by the specific heat by the change in temperature, okay? Now, one thing that I'm going to do with this one, all right, I don't expect you necessarily to do this every single time, but I want to do it this time to show you a couple of things about where we're ending up here. So, 500 grams is the mass, specific heat 4.18, and then it's got kind of a crazy unit, joules over grams times degrees Celsius. This is all the unit on specific heat, okay? And then finally, we know that the change in temperature is positive 80 degrees Celsius, okay? Now, numbers-wise, what are we going to do with the numbers? Multiply them all together, okay? So that'll be pretty easy. But let's talk units, right? Actually, Frank, did you multiply these numbers all together? What'd you get?
167,200.
Okay, 167,200, okay? Now, let's talk units, okay? We multiplied the numbers together, we have to multiply the units all together as well, okay? So if we do that, multiplying fractions together, we end up with this. Does that make sense? How that's what happens when we multiply the units all together? Right? So in this case, right, what's going to happen to the grams? They're going to cancel. What's going to happen to degree C? Cancel. And we're going to be left with what? And that's good because what is Q representing? Energy. And we measure energy in joules, right? Okay? So we know our unit's going to be joules. Okay? Now, even though I would never give you a problem like this, and we'll tell you why in a second, right? Let's make sure we're consistent with our process, and let's do significant digits, right? How many significant digits should this answer have? One, all right? I'm not going to do that to you on a test because that's lame, all right? But 500 without a decimal point is how many significant digits? One. This is how many? Three, right? And then here we end up with 80, and that's only how many as well? One, right? So we would have to round this to what? 200,000. Now, like I said, I wouldn't give you a question like that on a test because that's lame. I wouldn't do that to you. But if we're going to be consistent, that's what we have to do. Yes. All right. Good there? Gold has a specific heat of 0.130, which we already talked about. It says if 195 joules of heat are added to 15 grams of gold, how much does the temperature of the gold change? So what is this question asking us for?
Changing
All right, delta T is our unknown. Okay. It told us that gold has a specific heat of 0.130 joules over grams times degrees C. It says that 195 joules of heat are added. That's going to be what letter?
Q.
That's Q, right? Because Q is our heat energy, right? And then it tells us that the mass is 15 grams. Good there? Okay. So, here's our equation that relates the amount of energy that's added to the change in temperature. Okay. But, what are we trying to solve this for? Delta T. So, we could just plug the numbers in and then solve for delta T, or like we've discussed, we can rearrange this formula before we plug anything in. And if we do that, we end up with that, right? Good with that, how we manipulate that equation? Okay. All right, so now we plug things into this equation and solve for delta T. Oh, crap. Frank, did you run this through correctly? What'd you get? 100 exactly? Ooh, this is going to be a tricky one. Okay, first, did everybody get 100? Okay. All right, so this is a tricky one. According to our numbers, right, how many significant digits should our answer have? Should have 2. All right, so we can't do this, right? That's 3. We can't do this. That's 4, all right? We actually have a fallback plan. Does anybody remember what our fallback plan is in a situation like this? 10.0. 10.0 is a different number, right? And 10 is a different number. 10 is different than 100. Okay? So, say again? Not a fraction. But we can use scientific notation. Okay? Do you remember? First, we remember what scientific notation is. Right? Okay. So, remember that anything that we write in scientific notation is significant. Okay? How many places are we going to move the decimal to turn 100 into scientific notation? You're going to move it 2 places. So we're going to end up with times 10 to the 2nd power. Does that make sense? But how many significant digits are we supposed to have? 2. Okay? Does that make sense why that's 2 significant digits? But it's still 100. It's just 100 with 2 significant digits. Go ahead, Tim.
So you said everything in scientific notation is significant.
If we write anything in scientific notation, it would be significant.
So, but like then the 0 on the so
This 0 here, because we wrote it in scientific notation, is significant. Okay? But this isn't 10. This is still 100 because we would have to move that 2 places, right? So yeah, sorry. Yeah, this part of the scientific notation, the coefficient of scientific notation. Okay? Yeah, sorry, not the times 10 part. That's just the multiplier. Okay? Last thing, what kind of unit do you have on this?
Degrees Celsius.
Okay. Good there? Last one, do it yourself, go. I'll do it up on the board, and then you can. How's that? Okay. From a unit standpoint, right? If we look at the units that are over here, once we've rearranged this equation, we got joules on the top, we got grams on the bottom, we got degrees C on the bottom. None of that cancels, right? So all we do is just mash it all together into one big unit, and that's our unit on specific heat. Okay? Good there? All right, I'll tell you what. We will introduce the calorimeter tomorrow at the beginning of the period because it relates to what we're doing tomorrow in class. So we will take these calculations that we did today and we will apply them to an experimental situation tomorrow at the beginning of class. All right? Oh, if you take a look at the calendar, there are a couple of pages from the book that relate to specific heat and measuring heat changes. It's pretty much the equation that we went over in class today. Okay?